Okay, welcome to the deep dive.
Great to be here.
Today we're looking at, well, a really interesting bit of Selene history from the early 80s. A chip, or rather a chip family, that was technically pretty advanced, packed with features,
Mm,
but it didn't quite end up where you might expect in the big PC boom.
that's right. We're talking about Intel's 8186 and its sibling, the 8188. And our mission really is to figure out what made them special back then, why they got kind of leapfrogged by the 80286 for mainstream PCs, and where they actually ended up having a very long, successful career.
Right. And we've dug into the sources, the original Intel data sheets, which are always fun,
Oh, yeah.
historical articles, even some forum chats from people who actually, wrestled with these things back in the day. It's a great story about how sometimes the best tech specs bump up against market realities.
Yeah, compatibility is often king, isn't it?
It really is. So let's start there. Fundamentally, what was the 8186? Where did it sit in Intel's lineup at the time?
Okay, so think of it as the next logical step, maybe after the 8086 and the 8080. It's still a 16-bit processor at its core, built on that same basic architecture that, powered the original IBM PC, an enhanced version.
But just saying enhanced feels like it undersells it a bit, doesn't it? Because
Yeah.
the big deal with the 186 and what the sources really hammer home was this idea of integration. That was Intel's big push.
Absolutely. High integration. That was the buzzword.
Right.
See, back then, for a system using an 8086 or 8088, you needed like a whole bunch of separate chips surrounding the CPU just to make it work.
Right, support chips for everything.
Yeah, stuff like the clock generator, interrupt controllers, timers, DMA controllers, all separate little ICs on the motherboard. Intel's idea with the 8186 was, well, let's just build a lot of that common stuff right onto the processor die itself.
So functions that used to take up, what, half a dozen chips or more, suddenly just part of the CPU package?
Exactly. The data sheets list them out. You got a clock generator built in, 2 independent DMA channels, that's direct memory access.
Which lets peripherals move data around without bothering the CPU constantly.
Precisely. Big performance helper. Then there's a programmable interrupt controller, crucial for handling signals from devices. 3 programmable 16-bit timers. You always need timers for scheduling, generating sounds, that kind of thing.
Okay.
Plus, programmable chip select logic to simplify hooking up memory and peripherals. A wait state generator for slower devices, even a local bus controller. It's a lot of consolidation onto one piece of silicon.
Wow, yeah, just listing them out tells you something. It sounds like it was really aimed at making system designs simpler. Fewer chips needed, right?
That was the huge advantage they were pushing. Fewer chips means, well, simpler board layout, less power draw, maybe a smaller final product, and crucially, lower overall system cost. For certain applications, especially where cost and size are really tight, this was a game changer.
And did all this integration, plus maybe core improvements, mean better performance than the old 8086?
Oh yeah, definitely. The sources often quote something like, twice the performance of an 8086 running at the same clock speed. Some of that was just the core being a bit smarter, but a lot came from having dedicated hardware for certain tasks right on the chip.
Like what kind of tasks?
Things like calculating memory addresses that got faster, multiplication and division were significantly quicker because of internal hardware support. Same for shifting multiple bits at once. You weren't just relying on the main execution unit for everything.
Gotcha. Specialized hardware acceleration, basically. And what speeds are we talking about initially? Faster than the original PC's 888?
Oh yes, initial versions launched at I think 6, 8, and 10 megahertz. Remember, the IBM PC was chugging along at 4.77 megahertz with its 8088, and later, especially the CMOS versions, they pushed the 186 and the 188 up to even 25 megahertz over their very long lifespan.
And they didn't just tweak the hardware, they added some new instructions too, didn't they? Part of the by 86 evolution.
They did. Sometimes called the 8086 to an instruction set. They added things programmers found useful, like enter and leave for managing function calls, setting up and tearing down stack frames more easily.
Okay.
Push and pop-up, push all registers, pop all registers. Super handy for things like interrupt routines where you need to save the machine state quickly.
Yeah, I can see that being useful.
Then there was bound for checking array boundaries, ins and outs for faster input-output of strings of data. Plus they added immediate modes to some existing instructions, like you could push a constant value directly or multiply by a constant more easily. These weren't throwaway additions either. These instructions stuck around in the 8286 and later processors.
So enhancements on multiple fronts: hardware integration, core speed, and the instruction set itself. Now, we also mentioned the 8188. What was the difference there?
The 8188, internally almost identical. Same core improvements, same integrated peripherals, same new instructions. The big difference was the external data bus. The 8186 had a 16-bit path to memory and peripherals like the 8086. The 8188 used an 8-bit external data bus, just like the 8088 that was in the original IBM PC.
And the rationale there was mainly cost, I assume? Cheaper to build systems around it?
Exactly. An 8-bit bus needs fewer pins, simpler connections on the board, cheaper support chips potentially, especially if you're interfacing with lots of older 8-bit devices. Inside, it was still a 16-bit processor, could still address a megabyte of RAM, but getting 16 bits of data in or out took 2 steps instead of 1. So a bit slower externally, but cheaper to implement.
Okay, so summing up this part, you've got the 8186 and 8188. Faster, way more integrated, which simplifies design and cuts cost, useful new instructions. Looking at all that, it just screams next-generation PC processor, right?
Sure.
The obvious successor to the 8088.
It absolutely looks that way on paper, doesn't it? Logically, technically, it seems like the perfect fit.
Okay.
But, well, this is where the story pivots pretty sharply, because the mainstream PC market, it largely just skipped right over the 8186.
And that's the core puzzle. Why? With all those clear advantages, why didn't it become the heart of the next wave of PCs after the first IBM model?
And the answer, according to pretty much all the sources, comes down to one critical word: compatibility. Specifically, hardware compatibility with the design choices IBM made for that original PC.
Okay, unpack that. IBM used the 8088, but they surrounded it with specific support chips, right?
Exactly. IBM did just pick the 8088 CPU. They built an architecture around it, using a standard set of companion chips. Things like the Intel 8253 timer, the 8237 DMA controller, the 8259 interrupt controller. These external chips sat on the motherboard.
And they had specific addresses, like the software knew exactly where to talk to the timer chip, for instance.
Precisely. Those chips were mapped to specific standardized addresses in the PC's I/O address space. Now, remember how the 8186 integrated all those functions onto the chip?
Yeah. Oh, don't tell me Intel put their integrated versions at different addresses.
Bingo. That's the clash. The 8186's built-in timer, its built-in DMA, its built-in interrupt controller, they were designed to respond to I/O addresses that were different from the addresses used by those standard external IBM PC support chips.
Ah, okay, I see the problem. So if you built a machine with a 186 software written for a standard IBM PC, which expected to find the timer at, say, IO address X, would look at address X on the 186 machine
and find nothing, or maybe something completely unrelated. And conversely, the 186's integrated timer sitting at, say, address Y would be ignored by that standard software, which didn't know to look there.
It's a fundamental mismatch in the hardware layout expected by the software.
Exactly, an I/O address mapping conflict. Plus, there were apparently some differences in how video memory was typically handled, too. It meant that if you tried to build a PC around the 8186 and actually use its integrated peripherals to save cost and simplify the design, which was the whole point of the chip, that machine just wouldn't behave like a standard IBM PC at that low hardware level.
And in the early PC days, that kind of hardware incompatibility was poison for software, especially games and utilities that went straight to the metal.
Absolutely lethal. So much important software relied on those standard hardware addresses for the timer, DMA, interrupts. A system using the 186's integrated features just wouldn't present that expected hardware landscape. As one source described it, making a truly IBM PC compatible machine using the 8186's integrated features was near impossible, or, kind of pointless if strict compatibility was your goal.
You'd either have to ignore the built-in stuff and add the old external chips anyway,
Defeating the purpose and cost savings of the 186.
or just accept that your machine wouldn't run a chunk of standard PC software.
Right, and given how fast the IBM PC standard was taking over, compatibility was everything.
So what happened instead?
IBM needed a next-gen chip.
And they skipped the 186 family. For their next big machine, the IBM PCIe, they jumped straight to the Intel 80286. Now, the 80286 was more powerful in other ways, introduced protected mode, for instance, but crucially, it didn't have that same high level of peripheral integration as the 8186.
So the 80286 still relied on external support chips, similar to the original PC. Largely, yes. The PCS used newer versions of some support chips, but they often maintained compatibility with how the original PC's chips were addressed and behaved. This made it much easier to maintain backward compatibility with the existing software library. The 80286 fit the established PC architecture mold better, even if it wasn't as integrated as the 186 could have been.
So the market essentially chose compatibility with the established discrete chip architecture over the potential cost simplicity benefits of the 186's integration.
That's the long and short of it. IBM went with the 80286 The clone makers followed IBM, and the 8186 family, despite its technical merits, got relegated to the sidelines of the PC market.
Okay, so if the PC world wasn't its home, where did the 8186 and 8188 find their place? Because you said they had a long and successful life. That integration must have been valuable somewhere.
Absolutely. They found a massive, thriving market in exactly the area they were probably best suited for all along. Yeah. Embedded systems and dedicated controllers.
Right, not general purpose computers, but things where the computer is inside some other device doing a specific job.
Exactly that. Think about designing, say, a network router, or a piece of industrial control equipment, or even a fancy modem back then. What do you care about? Minimizing the number of components, keeping power consumption low, making it reliable, and hitting a specific cost target.
And the 186's integration, fewer external chips needed, fits that perfectly.
It was a perfect match. You didn't need to worry about strict IBM PCIO address compatibility because you were designing a custom system from the ground up for a specific task.
Sure.
The fact that the timer, DMA interrupt controller, and chip selects were already on the chip meant a simpler, smaller, cheaper board design. That's gold in the embedded world.
So the thing that killed it for the PC, the non-standard integrated peripherals, was actually its killer feature for embedded.
Pretty much. It was designed to be the brains of a dedicated device, not a general-purpose PC needing to run off-the-shelf DOS games. And the sources list tons of examples where they were used. You see them inside modems. The Intel 14.4EX is a well-known one, FX cards, protocol converters like the IBM 7171 that help mainframes talk to other things. Even sophisticated devices like the DEC Detox speech synthesizer apparently had an 8186 core. And controllers too, right, like for lab equipment or manufacturing?
Yes, and things like in-circuit emulators. The Microtech 8086 emulator is mentioned, tools used by engineers to develop other systems. Basically, anywhere you needed decent 16-bit processing power and integrated I/O without needing full PC compatibility or the complexity of a full PC motherboard.
Okay, that makes sense. But you did say a few actual personal computers use them, even with the compatibility headaches.
Yes, there were some interesting attempts, and they kind of highlight the trade-offs. The Tandy 2000 is probably the best-known example in the U.S.
Right, I remember those. They looked quite advanced. They were. Using 8186, ran faster than standard PCs, had options for better graphics, could address more RAM natively. I think someone even figured out a mod to get 896 key B usable under DOS, which was huge then.
The catch.
The catch was compatibility. Because it leaned on the 186's architecture and wasn't fully IBM BIOS compatible, especially around video, a fair amount of popular IBM PC software just wouldn't run correctly or at all. Great hardware hampered by the ecosystem.
The classic story. Any others?
Yeah, there was either the RM Nimbus, popular in UK schools, which wasn't fully PC compatible. A Canadian school computer, the Unisys Icon, used the 8186 but primarily ran the QNX operating system, not DOS. Siemens in Germany had the PCD, which was described as almost compatible and offered more RAM.
And those HE Palm Tops, the 100LX, 200LX, those were quite popular for a while.
They really were. Used a low-power CMOS version, the ADC-186.
Yep.
They ran MS-DOS 5 and were surprisingly capable of running a lot of 800-868-186 software, even some 286 stuff if it didn't use protected mode. A fantastic niche product showing where the 186 could fit, especially when power and integration were key.
There were even accelerator cards, right? Like plugging a 186 into your original PC.
Yep. Orchid Technology made the PC Turbo 186. It gave your old PC an 8186 boost, though again sometimes with compatibility quirks depending on how software interacted with it. But yeah, despite these niches and valiant efforts, the 186 family just never cracked the mainstream PC market code. That path was firmly set on the 8088 and 8786 Natch 386 trajectory.
And eventually, even that incredibly long run in the embedded world came to an end for the 186 family.
It did, remarkably late though. Intel finally announced they were discontinuing production back in March 2006.
Wow, 2006.
Yeah, with the very last shipments going out in September 2007. That's what, almost 25 years after its introduction. An incredibly long life for a microprocessor architecture, especially one that missed the PC wave, mostly humming away inside devices you never really thought about.
So wrapping up this deep dive on the 8186 and 8188, it's a fascinating story, isn't it? You have this chip that technically offered real advantages: speed, that clever integration simplifying system design, cutting costs.
All things that seem like winners.
But because that very integration broke step with the hardware standards being rapidly cemented by the IBM PC, it got sidelined in that huge defining market.
Only to find this massive, decades-long success story. in a completely different area, embedded systems where its specific strengths were exactly what was needed. It really drives home that tech success isn't just about having the best specs in a vacuum.
Yeah, it's about the ecosystem, the standards, the path dependency, how things connect or don't connect.
Right. Compatibility, timing, market forces, they shape which technologies take off and where.
Absolutely. It makes you pause and think, doesn't it? How different could things have been if IBM had somehow designed the original PC around the 186's integrated approach? Would we have had simpler, cheaper PCs earlier?
Or maybe a more fragmented market. It's hard to say. But it certainly makes you wonder about other examples, maybe less obvious ones, where a technically neat idea got pushed aside because it just didn't fit the dominant standard at the right time. What other tech battles like that come to your mind?